Tonight, we're exploring some of the strangest secrets about black holes. Objects powerful enough to bend time, trap light, and make scientists constantly question the true nature of the universe. What do you think is really hiding inside a black hole? And what city are you watching from tonight? Leave it down in the comments below. If you enjoy relaxing cosmic mysteries like this, don't forget to subscribe, because tonight's journey is taking us far beyond the edge of known space. Out there tonight, somewhere beyond the reach of human eyes, a star may already be dying. Not quietly, not peacefully, but under a pressure so extreme that the laws of ordinary life no longer make sense. For millions of years, that star spent its existence resisting collapse. Gravity kept trying to drag everything inward, while nuclear fusion pushed outward with enormous force. It was a balance so delicate that even a slight change inside the core could destroy the entire structure. And eventually, that balance always fails. One of the first strange truths about black holes is that most stars never become one at all. The night sky makes the universe look crowded with endless suns, but the majority will die much more gently. Smaller stars cool into white dwarfs. Others collapse into neutron stars, so dense a spoonful would outweigh mountains on Earth. Only the most massive stars, stars dozens of times heavier than our Sun, are capable of collapsing far enough to create a black hole. In a strange way, black holes are rare cosmic accidents born from the largest and most unstable stars nature can produce. But once those stars begin dying, the process becomes terrifyingly fast. Near the end of its life, a giant star starts running out of fuel in its core. Fusion slows down. The outward pressure weakens, and gravity immediately notices. The collapse begins so quickly that the core can implode in less than a second. Matter crashes inward at enormous speeds. Temperatures surge. Pressure rises beyond anything humans can reproduce naturally on Earth. Then, the outer layers explode outward in a supernova so bright it can briefly outshine entire galaxies. Ancient astronomers saw these explosions without understanding them. New stars suddenly appeared in the sky where darkness existed before. Some civilizations believed they were omens. Others thought the heavens themselves were changing. What nobody knew was that hidden inside certain supernovas, after the light faded, something darker remained behind. The truly frightening moment comes when gravity becomes stronger than escape itself. Every object has an escape velocity, the speed required to break free from its gravity. Earth has one. The Sun has one. But if enough matter collapses inward, there comes a point where escape velocity exceeds the speed of light. And because nothing can travel faster than light according to modern physics, nothing can leave anymore. Not dust, not radiation. Not even light itself. That idea sounds modern, but surprisingly, humans imagined it centuries ago. In the late 1700s, an English scientist named John Michell wondered whether a star could become so massive that light would fail to escape its gravity. He called them dark stars. At the time, the idea seemed bizarre because people still barely understood what light actually was. The universe felt orderly then, predictable. Invisible stars hiding in space sounded closer to fantasy than astronomy. Then Einstein arrived and made the idea even stranger. General relativity transformed gravity from a force into something deeper. Massive objects bent space and time themselves. A star was no longer simply floating in space, it was warping reality around it. And buried inside Einstein's equations was a terrifying implication. If enough mass collapsed inward, spacetime could curve so severely that it sealed itself off from the rest of the universe. Even Einstein reportedly struggled with that conclusion. Soon after the theory was published, physicist Carl Schwarzschild discovered a mathematical solution describing an object whose gravity trapped light permanently. Today, scientists call the critical boundary surrounding that object the event horizon. But the disturbing thing is that the event horizon is not a physical surface. There is no wall, no edge, no dramatic barrier glowing in space. And that is what makes it so psychologically unsettling. You would not crash into anything crossing it. In fact, depending on the size of the black hole, you might not notice the exact moment at all. Space could appear strangely calm. The stars might still shine around you. Yet, beyond that invisible line, escape becomes impossible. Not because of chains or force fields, but because space-time itself bends inward too steeply. The universe stops offering outward directions. That idea feels less like ordinary danger and more like reality malfunctioning. And despite all this, black holes are often much smaller than people imagine. A stellar black hole containing several suns' worth of mass may only span a few dozen miles across. Something smaller than a city can outweigh stars. Human intuition breaks down completely at that scale because nothing in normal life prepares the brain for densities like that. Mountains feel massive to us. Oceans feel enormous. Yet black holes compress matter so tightly that ordinary comparisons stop working. Some physicists describe the collapse almost like the universe folding inward under its own weight. Oddly enough, black holes are not dangerous because they suck everything toward them like giant cosmic vacuum cleaners. That image became popular in movies, but gravity behaves more subtly than that. If the sun were somehow replaced by a black hole with the exact same mass, Earth would continue orbiting almost normally. We would lose sunlight, temperatures would collapse, life would eventually freeze. But our planet would not suddenly spiral into destruction. At Earth's distance, gravity would remain nearly identical. That realization changes black holes from monsters into something colder and stranger. They do not need to hunt. They simply exist, quietly bending reality around themselves. And most may remain almost completely invisible. Astronomers believe the Milky Way alone could contain millions of black holes created by ancient dead stars. Most emit no light. Many drift silently through interstellar darkness, undetected unless they interact with nearby gas or stars. Somewhere between the visible stars of our galaxy may exist countless unseen gravitational ghosts wandering through the dark. That possibility subtly changes the emotional feeling of space itself. The night sky begins seeming less empty, but also less safe. Darkness may not actually be empty darkness at all. And some black holes may be far older than the stars around them. One of the most fascinating theories in cosmology suggests certain black holes formed not from dying stars, but from the chaos immediately after the Big Bang. In the newborn universe, Matter was compressed into densities almost impossible to imagine. Tiny fluctuations may have collapsed directly into primordial black holes before galaxies even existed. These hypothetical objects could range from microscopic sizes to enormous masses. Scientists still debate whether primordial black holes are real. Evidence remains incomplete, but if they exist, they may help explain mysteries surrounding dark matter, the invisible substance believed to shape much of the universe's structure. And that possibility leads to another unsettling mystery. Some supermassive black holes discovered in the early universe appear far too large for current theories to explain comfortably. Astronomers have observed gigantic black holes already existing surprisingly soon after the Big Bang, at a time when the cosmos itself was still young. According to standard models, they may not have had enough time to grow that large naturally, which raises difficult questions. Did black holes grow faster in the early universe? Did unknown physical processes exist shortly after the Big Bang? Or are scientists still missing something fundamental about how black holes form? The deeper researchers investigate, the stranger the story becomes. Black holes repeatedly appear at the edge of modern understanding, where relativity, quantum physics, thermodynamics, and cosmology begin colliding with each other. They are not simply objects in space anymore. They are pressure points in reality itself. And perhaps that is why black holes continue haunting human imagination so deeply. Not because they destroy stars, but because they expose how fragile human understanding really is. The closer science gets to them, the more familiar ideas begin breaking apart. Space, time, escape, even the meaning of direction itself. Somewhere tonight, another massive star is likely nearing collapse. Deep inside its core, gravity is slowly gaining control. The balance is fading. Soon, maybe tomorrow, or maybe thousands of years from now, that star will implode inward faster than anything humans experience on Earth. A supernova will erupt outward. Radiation will race through space. And hidden inside the aftermath, another invisible region may quietly appear in the cosmos. A place where dead stars stop being stars at all and become something darker than darkness itself. There is a strange moment in modern physics when time stops behaving like something humans naturally understand. Not because clocks fail or because technology breaks, but because the universe itself begins treating time differently depending on where you are standing. And nowhere does that become more unsettling than near a black hole. For most of human history, time felt permanent. Ancient civilizations measured it through shadows, seasons, lunar cycles, and the movement of stars. Even after mechanical clocks appeared, people still imagined time as universal, something flowing equally everywhere like an invisible river carrying the entire cosmos forward together. It was comforting to think that a second on Earth was the same as a second anywhere else in the universe. Then, Einstein quietly destroyed that idea. One of the most important consequences of general relativity is that gravity affects time itself. The stronger gravity becomes, the slower time moves relative to places farther away. This is not science fiction anymore. It has been measured repeatedly. Even satellites orbiting Earth experience tiny differences in time compared to clocks on the ground. GPS systems must constantly correct for relativistic effects, or navigation would drift miles off course. But Earth's gravity is weak compared to what exists near a black hole. Close enough to one, time distortion becomes so extreme that ordinary intuition starts collapsing completely. Imagine drifting near the edge of a massive black hole while carrying a simple wristwatch. To you, the watch appears normal. Your heartbeat feels normal. Thoughts move normally. Nothing inside your body tells you time has changed. Yet for someone watching safely from far away, your clock would appear slower and slower. Near certain black holes, a single hour for you could equal years somewhere else. That idea became widely known through the film Interstellar, but the underlying science was grounded in real physics. The fictional planet orbiting close to the black hole Gargantua experienced such powerful gravitational time dilation that 1 hour on the planet equaled 7 years back on Earth. The numbers in the movie were dramatized carefully, with help from physicist Kip Thorne, who worked to keep the extreme visuals scientifically plausible. And emotionally, that concept feels heavier than most science fiction. Not because it involves complicated equations, but because it quietly changes the meaning of separation. A person could leave near a black hole and return to discover entire generations gone, families aged, civilizations changed, languages evolved. The traveler barely older than before, while the universe moved on without them. Black holes turn time itself into distance. And perhaps the strangest part is that the person near the black hole would not feel trapped inside slow motion at all. Human consciousness experiences time locally. Your thoughts still arrive one after another normally, from your own perspective. The distortion only appears when compared to another observer farther away from the gravitational field. This creates one of the most unsettling consequences of relativity. Two people can experience entirely different amounts of time while both being correct. In ordinary life, humans rarely question time because our experiences remain synchronized closely enough to hide these differences. But black holes expose something uncomfortable. Time is not universal. It bends. And under enough gravity, it bends dramatically. Some physicists have even described black holes as natural machines for traveling into the future. Not backward through time in the cinematic sense, but forward. If a spacecraft could orbit safely near a supermassive black hole without being destroyed by radiation or tidal forces, the crew might experience far less time than observers elsewhere. They could effectively leap forward into the distant future of the universe. Theoretically, someone could leave Earth and return thousands of years later while aging only a fraction of that time personally. But black holes distort more than clocks. Near the event horizon, light itself begins behaving strangely. Photons, climbing away from intense gravity, lose energy, stretching into longer and redder wavelengths through a process called gravitational redshift. To distant observers, light escaping near a black hole appears dimmer, redder, and slower over time. Eventually, it fades almost completely. That fading creates one of the eeriest visual effects in astrophysics. If you watched someone fall toward a black hole from far away, they would appear to slow down more and more near the event horizon. Their movements would stretch, their signals would weaken, their image would redden and darken until they seemed frozen near the boundary forever. From the outside, it almost looks like the black hole never fully allows anything inside. But from the perspective of the falling person, something entirely different happens. Assuming the black hole is large enough to avoid immediate tidal destruction, the traveler may pass through the event horizon without noticing any obvious physical boundary at all. There is no wall waiting there, no sudden impact. Space may still look relatively normal for a brief time. Stars might continue shining overhead. The terrifying realization is that the point of no return is mathematically real while remaining visually invisible. Nothing appears different until escape no longer exists. That subtlety makes black holes psychologically disturbing in ways explosions or disasters are not. Human beings evolved to recognize danger visually. Fire spreads. Storms darken skies. Predators reveal themselves physically. But near a black hole, reality itself becomes the trap. And once inside, modern physics becomes increasingly uncertain about what happens next. According to general relativity, space-time curves inwards so severely beyond the event horizon that all future paths lead toward the singularity. In ordinary life, forward feels like a direction humans choose freely. But inside a black hole, some physicists describe moving toward the singularity as unavoidable as moving toward tomorrow. The geometry of space-time itself changes. That idea is difficult to visualize because humans think spatially, not relativistically. But near black holes, space and time stop behaving independently. Distances warp. Causality distorts. The universe begins acting less like a stable environment and more like a structure under extreme tension. And light reveals that distortion beautifully. Around certain black holes exists a region called the photon sphere, where gravity bends light into looping paths. Photons can orbit the black hole temporarily before escaping or falling inward. This bending effect creates warped rings of light surrounding darkness itself. Entire galaxies behind a black hole may appear stretched, duplicated, or curved into glowing arcs. When astronomers released the first image of a black hole's shadow in 2019 using the Event Horizon Telescope, many people expected something dramatic, perhaps a visible hole tearing through space. Instead, the image revealed something quieter and somehow more unsettling. A dark center surrounded by a ring of distorted light, glowing because gravity itself was twisting the paths photons traveled. It looked less like destruction and more like reality bending. And even that image only showed the outside. Nobody knows what truly happens to time deeper inside a black hole, because current physics begins breaking apart near the singularity. According to relativity, density may become effectively infinite there. Space-time curvature may also become infinite. The equations stop producing meaningful answers. This is one reason black holes fascinate physicists so deeply. They sit directly at the border where humanity's two greatest scientific frameworks, general relativity and quantum mechanics, stop fitting together comfortably. Relativity describes the large-scale structure of gravity beautifully. Quantum physics explains the microscopic world with astonishing accuracy. But inside black holes, both theories begin conflicting with each other, and that suggests something profound. Humanity's understanding of reality may still be incomplete. Some researchers suspect singularities never truly exist in nature, and that a future theory of quantum gravity will eventually replace them with something less paradoxical. Others think black holes may connect to wormholes, holographic principles, or structures not yet fully imagined. There is no scientific consensus yet, only competing possibilities trying to explain what happens where observable physics disappears. And perhaps that uncertainty is what makes black holes feel so haunting emotionally. They are not merely giant objects in space. They are regions where familiar concepts begin dissolving. Distance, escape, direction, even time itself. Somewhere tonight, near the center of a distant galaxy, a star may already be orbiting too close to a black hole. Its light stretched redder with every passing orbit, its clock running slower compared to the wider universe beyond. And around that invisible darkness, time itself may already be bending quietly into shapes human beings were never evolved to understand. Imagine drifting alone through deep space toward a region where the universe itself appears damaged. No explosions, no sound. Only darkness ahead, surrounded by warped light bending into impossible shapes. Your spacecraft instruments still function normally. Your heartbeat remains steady. From inside the cabin, nothing feels dramatically different yet. And that may be the most unsettling part about approaching a black hole. Reality often looks calm long before it becomes lethal. Most people imagine a black hole as a giant mouth instantly swallowing anything nearby. But if a human being ever truly approached one, death would probably begin long before crossing the event horizon itself. Around many black holes exists an accretion disk, a rotating structure of gas, dust, shattered asteroids, and sometimes entire stars being torn apart by gravity. As matter spirals inward, friction and compression heat it to extraordinary temperatures. Some regions become hotter than the surface of stars. Radiation erupts outward in powerful X-rays and gamma rays capable of sterilizing nearby space. In other words, the darkness of a black hole is often surrounded by some of the brightest and most violent environments in the universe. A spacecraft approaching too closely would likely encounter deadly radiation first. Electronics could fail. Biological tissue would absorb enormous energy. Long before a person reached the event horizon, the environment itself might already become unsurvivable. In a strange way, black holes are not isolated killers. The chaos surrounding them often does the work first. But suppose technology advanced enough to shield against that radiation. Suppose someone continued inward anyway. The visual experience alone would become deeply unnatural. Gravity near a black hole bends the paths of light so severely that the sky itself would appear distorted. Stars behind the black hole could curve around it into glowing arcs. Some regions of space might seem duplicated or stretched. Darkness would not simply look black anymore. It would look wrong, as if space had folded inward around an invisible center. This effect, known as gravitational lensing, has been observed throughout the universe, but near black holes it becomes extreme. Light no longer travels in what humans instinctively think of as straight lines. Instead, gravity reshapes the geometry through which light moves. The result is strangely dreamlike. The closer you drift toward the black hole, the less the universe resembles ordinary space. And eventually, gravity stops affecting only light. It begins affecting your body differently from one end to the other. This happens because gravity weakens with distance, and near a black hole, the difference between closer and farther can become enormous across even a human body. If your feet are slightly nearer to the black hole than your head, gravity pulls harder on them. At first, the difference might be subtle, but closer in, the imbalance increases rapidly. Scientists call these tidal forces. and tidal forces can become catastrophic. The process has one of the strangest names in astrophysics: spaghettification. As tidal forces intensify, your body would begin stretching vertically while compressing sideways. Gravity would pull more strongly on the lower half of your body than the upper half, gradually elongating you into something thinner and longer. Molecules themselves could eventually separate under the stress. Oddly enough, smaller black holes may kill faster this way than supermassive ones. That sounds backward at first. Intuition suggests larger black holes should always be more violent. But near stellar black holes, tidal forces become deadly before even reaching the event horizon, because the gravitational gradient changes so sharply over short distances. Supermassive black holes, on the other hand, spread their gravitational effects across vastly larger regions. In theory, someone crossing the event horizon of a supermassive black hole might survive the crossing itself temporarily without immediately noticing physical destruction. And that possibility creates one of the most psychologically disturbing ideas in modern astrophysics. You might not realize when you crossed the point of no return. The event horizon is not a physical surface. There is no impact, no wall, no visible crack in space announcing that escape has become impossible. Assuming the black hole is large enough and conditions are calm enough, the crossing could feel almost ordinary for a brief moment. Stars might still shine outside the spacecraft windows. Your watch might continue ticking normally. The cabin air might remain perfectly still. And yet, every future path available to you would now lead deeper inward. That subtle horror makes black holes different from nearly every danger humans evolved to understand. Predators reveal themselves. Storms announce their arrival. Fires spread visibly. But the event horizon hides its danger inside mathematics itself. Nothing changes visually at the exact moment escape disappears forever. And from far away, outside observers would witness something entirely different happening to you. According to general relativity, extreme gravity distorts time so severely near a black hole that distant observers would see your movements slowing down near the event horizon. Signals from your spacecraft would stretch and redden. Your image would gradually dim. To them, you would appear frozen near the boundary, fading slowly over time without ever fully crossing it. From their perspective, the black hole almost seems unwilling to let you vanish completely. But from your own perspective, time continues normally. You keep falling inward. This creates one of the strangest observer paradoxes in science. Two different realities coexist depending on viewpoint, and both are mathematically valid. For the outside universe, you linger near the event horizon almost endlessly. For yourself, the descent continues toward the center. And during that descent, something extraordinary might happen visually. Because of extreme time dilation, light from the external universe could appear accelerated ahead of you. In theory, you might watch stars aging faster than normal, galaxies evolving, cosmic events unfolding in compressed form. Some physicists speculate that an observer falling deep enough toward a black hole could witness portions of the universe's future unfolding rapidly outside. Exactly how much could be seen remains uncertain because radiation, tidal forces, and the internal geometry of the black hole complicate the situation enormously. But the possibility itself feels haunting. Drifting toward destruction while watching the rest of the universe race forward in time. Eventually, though, every known path leads toward the singularity. And this is where physics begins losing clarity. According to Einstein's equations, the singularity is a point where density becomes effectively infinite, and space-time curvature also becomes infinite. But infinities in physics often signal that a theory has reached its limit, rather than describing literal reality perfectly. Most scientists suspect modern equations become incomplete near singularities. In other words, humanity does not truly know what exists there. General relativity predicts collapse continuing indefinitely inward. Quantum mechanics suggests something more complicated may occur. But the two theories remain fundamentally incompatible in these conditions. Black holes sit precisely where the largest structures in physics and the smallest structures in quantum reality begin colliding with each other. And because of that, black holes remain less understood than many people realize. Some theories suggest singularities may never fully form. Others propose quantum effects create new structures deep inside black holes. A few speculative models even suggest black holes could connect to wormholes or entirely separate regions of spacetime, though there is no observational evidence confirming such ideas. Still, the fact that scientists seriously debate these possibilities reveals how incomplete modern understanding remains. Black holes are not simply cosmic objects anymore. They are boundaries around human knowledge itself. Perhaps that is why the idea of falling into one feels so emotionally powerful. It combines physical danger with something deeper, the sensation of moving toward a place where familiar reality stops functioning properly. Space bends, time distorts, light curves, direction loses meaning. The closer you move toward the center, the more the universe begins behaving unlike the universe humans evolved to recognize. And somewhere tonight, beyond the visible stars above Earth, matter may already be spiraling inward toward another black hole. A dying star stretched apart into glowing streams, radiation erupting outward into surrounding darkness, gravity pulling harder and harder with every passing second. And beyond the invisible boundary surrounding that darkness, space-time itself may already be folding inward toward a region no human mind has ever truly understood. Beyond the event horizon, the universe may stop behaving in ways human beings can truly picture. Not visually at first, not dramatically. There may be no glowing tunnel, no violent transition, no sudden collapse into cinematic chaos. But deeper inside a black hole, according to modern physics, something far stranger begins happening. The equations that normally describe reality itself start breaking apart. And that may be the most unsettling secret black holes have revealed so far. For centuries, science progressed by assuming nature could ultimately be explained through consistent rules. Planets followed predictable orbits. Gravity obeyed mathematical patterns. Light traveled according to measurable laws. Even when discoveries became surprising, scientists still trusted that reality underneath remained logically structured. But black holes introduced a place where those rules seem to collide with each other. At the center of a black hole, general relativity predicts the existence of a singularity, a region where matter collapses into effectively infinite density and space-time curvature becomes infinite as well. That word, infinite, immediately alarms physicists because infinities in equations often signal something deeper is wrong or incomplete. Nature rarely behaves in truly infinite ways. More often, infinities appear when a theory reaches conditions it was never designed to handle. And black holes push physics precisely into that territory. Einstein's equations describe gravity extraordinarily well across stars, galaxies, and even much of the visible universe. But near singularities, those same equations stop producing meaningful predictions. Space and time themselves curve inward without limit. Distances shrink toward zero. The mathematical structure describing reality begins collapsing under its own implications. In a strange way, the singularity represents less of an answer and more of a warning sign. It may not be telling scientists what exists inside black holes. It may be telling them their understanding remains unfinished. That possibility has haunted theoretical physics for decades because it suggests one of humanity's greatest scientific achievements, general relativity, eventually breaks down under extreme enough conditions, and black holes expose that weakness mercilessly. Some physicists suspect singularities never truly exist in nature at all. Instead, they may simply mark the point where quantum effects become too important to ignore. Modern physics still lacks a complete theory of quantum gravity, a framework capable of uniting Einstein's large-scale description of gravity with the microscopic behavior of quantum mechanics. And without that missing theory, the interior of black holes remains deeply uncertain. This uncertainty changes the emotional feeling of black holes completely. They stop being merely dangerous objects and become places where human knowledge itself fades into darkness. It is difficult to think of another region in science where so much confidence disappears so quickly. The deeper researchers explored black holes mathematically, the stranger the implications became. According to general relativity, inside the event horizon, space and time may begin exchanging roles in disturbing ways. Outside a black hole, moving forward through time feels unavoidable, while movement through space remains flexible. You can choose directions in space, but you cannot stop traveling into tomorrow. Inside a black hole, some solutions to Einstein's equations suggest the singularity becomes as unavoidable as the future itself. In other words, falling inward may no longer feel like moving through space. It may resemble moving toward a moment in time that cannot be escaped. That idea is almost impossible for the human mind to visualize naturally, because human intuition evolved in weak gravity under ordinary conditions. Black holes force reality into shapes the brain was never designed to experience. Direction itself begins losing familiar meaning, and it is exactly there where space-time becomes deeply distorted that wormholes emerge from the mathematics. Wormholes are often treated like science fiction shortcuts through space, but the idea actually originates from legitimate solutions to Einstein's equations. In the 1930s, Einstein and physicist Nathan Rosen explored the possibility of bridges connecting distant regions of space-time. These hypothetical structures became known as Einstein-Rosen bridges. The concept is seductive because it hints at something extraordinary. Perhaps space-time can fold in ways allowing distant parts of the universe to connect directly. Instead of crossing billions of miles normally, one might theoretically pass through a tunnel linking separate regions together. But mathematics allowing something is not the same as nature permitting it physically. Most wormhole models appear catastrophically unstable. The moment ordinary matter enters, the structure may collapse almost instantly. Some theories suggest maintaining a traversable wormhole would require exotic forms of matter possessing negative energy density, something never observed in usable quantities. Still, physicists continue studying the possibility because the equations themselves refuse to dismiss it entirely. And once the idea of wormholes enters the conversation, black holes stop feeling like dead ends. They begin sounding more like doors. Some speculative theories even suggest black holes could connect to entirely separate universes. In certain cosmological models, collapsing matter inside a black hole might create conditions similar to those surrounding the Big Bang itself. Instead of ending in destruction, the collapse could potentially bounce into the birth of a new expanding spacetime region, effectively creating a baby universe disconnected from the original one. There is no observational proof for this idea. Many physicists remain skeptical. But the reason such theories survive at all is because black holes and the Big Bang already share strange similarities mathematically. Both involve extreme density. Both involve singularities in current equations. Both represent boundaries where modern physics loses clarity. And that resemblance has led some scientists to wonder whether our own universe could itself have emerged from conditions inside another black hole somewhere beyond our observable reality. It is one of those ideas that sounds almost philosophical until you realize it emerges from serious attempts to reconcile gravitational physics mathematically. If true, the implications become emotionally overwhelming very quickly. Our universe would no longer feel like the whole stage of existence. It might simply be one region hidden inside something much larger. And black holes would stop being cosmic graves. They would become engines of creation. Yet, even before reaching such speculative territory, black holes already generate another enormous scientific crisis: the information paradox. According to quantum mechanics, information about physical systems cannot truly disappear. Matter can change form. Objects can break apart. But the fundamental information describing those systems should remain preserved in some way. Black holes seem to violate that principle. If something falls into a black hole, and the black hole later evaporates over unimaginable timescales, what happens to the information describing what fell inside? Does it vanish permanently? If so, quantum mechanics may be incomplete. But if information survives somehow, where is it stored? This paradox became even more serious after Stephen Hawking demonstrated in the 1970s that black holes are not perfectly black after all. Through quantum effects near the event horizon, black holes can slowly emit radiation and eventually evaporate. That discovery shocked physics because it connected gravity, thermodynamics, and quantum mechanics together in ways scientists had not expected. And it forced researchers to confront an unsettling possibility. Reality might preserve information in ways humans still barely understand. One proposed solution suggests information about objects falling into a black hole may somehow become encoded on the surface of the event horizon itself. This idea contributed to the development of the holographic principle, the concept that information describing a three-dimensional region might actually be stored on a lower dimensional boundary. At first glance, The idea sounds absurdly abstract, but modern theoretical physics increasingly treats information as something deeply fundamental, perhaps even more basic than space itself. And that possibility changes how black holes are viewed once again. Instead of simple destroyers, they may function more like cosmic storage systems, hiding information in forms humanity cannot yet fully decode. The deeper science pushes into black holes, the more reality begins resembling something stranger than classical matter moving through empty space. Information, geometry, entropy, quantum uncertainty, and spacetime all begin blending together. Black holes sit exactly at that intersection. They are where familiar categories stop separating cleanly. And maybe that is why they continue pulling at human imagination so powerfully. Not only because they are dangerous, but because they hint that the universe underneath ordinary experience may operate according to principles far stranger than humans ever expected. Somewhere tonight, beyond the visible stars above Earth, another black hole may already be swallowing matter silently. Light bending around invisible gravity, time distorting deeper inside. And far beyond the event horizon, where current equations begin collapsing into uncertainty, the true structure of reality may already look nothing like the universe human beings believe they know. For a long time, black holes seemed almost eternal. They swallowed light, trapped matter, bent time itself, and hid everything behind an invisible boundary the universe refused to let anything escape. In many ways, they felt less like ordinary objects and more like permanent wounds in spacetime, regions so final that even physics appeared to lose track of what happened inside them. Then, Stephen Hawking introduced an idea so strange that it changed black holes forever. According to classical physics, a black hole should only grow larger. Matter falls inward. Energy disappears behind the event horizon. Nothing comes back out. The black hole simply accumulates more mass over time, like a cosmic prison with no exit. But quantum mechanics refuses to leave empty space truly empty. Even the vacuum of space is constantly fluctuating at microscopic scales. Tiny particle pairs briefly appear and vanish everywhere throughout the universe. Normally, these particles annihilate each other almost instantly, returning the borrowed energy back into the vacuum. But near the event horizon of a black hole, Hawking realized something unusual might happen. Gravity there becomes so extreme that one particle could fall inward while the other escapes before annihilation occurs. To distant observers, it would appear as though the black hole itself emitted faint radiation. That idea became known as Hawking radiation, and the implications were astonishing. Black holes were not completely black after all. At first glance, Hawking radiation almost sounds harmless. The radiation emitted by large black holes would be incredibly weak, far colder than the temperature of deep space itself. A supermassive black hole drifting between galaxies would absorb more cosmic background radiation than it emitted. Nothing dramatic would happen visibly, but over unimaginable timescales, something subtle begins changing. If a black hole emits energy, it loses mass. And if it keeps losing mass long enough, eventually, the black hole itself may disappear. This transformed black holes from eternal cosmic endpoints into temporary objects with lifespans, extremely long lifespans. A stellar black hole could survive for periods vastly longer than the current age of the universe. Supermassive black holes may persist for numbers of years so enormous the human brain struggles to emotionally process them. By the time many black holes fully evaporate, ordinary stars will already be gone. Galaxies will have faded. Much of the visible universe may drift into darkness and isolation. In some models of the far future, black holes become among the last surviving large structures in existence. That thought changes the emotional atmosphere of the cosmos entirely. Human civilization measures history in centuries. Recorded civilization itself spans only thousands of years. But black holes may outlive stars by durations so extreme that current cosmic history becomes almost microscopic in comparison. And yet, even they may not last forever. The smaller the black hole, the faster Hawking radiation removes mass. As a black hole shrinks, its temperature increases, causing evaporation to accelerate. In theory, tiny black holes could eventually release energy violently during their final moments. Some physicists have speculated that primordial black holes formed shortly after the Big Bang might already have evaporated long ago in bursts of gamma radiation. Astronomers have searched for evidence of such explosions, though no confirmed detection exists yet. The universe may contain traces of ancient black holes dying in sudden flashes billions of years ago. There is something strangely poetic about that possibility. Objects once considered the darkest things in the universe may ultimately end in light. But Hawking radiation created a much deeper problem than black hole mortality. It threatened one of the central foundations of modern physics. Quantum mechanics strongly suggests information cannot truly disappear from reality. Physical systems evolve, matter changes form, but the underlying information describing those systems should remain preserved somehow. If information could vanish completely, the predictability underlying quantum theory would begin breaking down. Black holes seem to challenge that principle directly. Imagine throwing a book into a black hole. The physical object disappears behind the event horizon. Over enormous timescales, the black hole eventually evaporates through Hawking radiation. But Hawking's original calculations suggested that radiation carried no detailed information about what fell inside. The information describing the book appeared permanently destroyed. That conclusion deeply disturbed physicists because it implied a contradiction between general relativity and quantum mechanics, the two most successful frameworks in modern science. And neither theory seemed willing to surrender. The debate became known as the black hole information paradox. For decades, some of the world's leading physicists argued over whether information truly disappears inside black holes or survives in some hidden form. Stephen Hawking himself initially defended the idea that information could genuinely be lost. Other physicists strongly disagreed, insisting quantum mechanics forbids such destruction fundamentally. At stake was not merely the behavior of black holes, but the consistency of reality itself. Because if information can disappear completely, then cause and effect may no longer function predictably at the deepest levels of physics. The paradox eventually became so famous that Hawking made public bets with other scientists regarding the outcome. Years later, he partially changed his position, acknowledging growing evidence that information might somehow survive after all. But exactly how remains unresolved. And this uncertainty pushed theoretical physics into even stranger territory. One possible solution emerged from studying black hole entropy, a measure of information and disorder associated with physical systems. Physicists Jacob Bekenstein and Stephen Hawking discovered something remarkable. The entropy of a black hole appears proportional not to its volume, but to the surface area of its event horizon. That detail sounds technical at first, but its implications are enormous. Ordinarily, humans expect information about an object to exist throughout its interior. Yet black holes hinted that information describing a region of space might somehow be encoded on its boundary instead. This insight helped inspire the holographic principle, the idea that three-dimensional reality may fundamentally behave like information stored on a lower dimensional surface. In simpler terms, the universe might work less like solid objects moving through empty space and more like a projection emerging from deeper informational rules. The idea feels almost surreal because it reverses ordinary intuition completely. Space stops being the stage where information exists. Information may instead become the thing from which space itself emerges. And black holes were among the first objects forcing scientists to consider that possibility seriously. Some modern theories even suggest spacetime itself could arise from patterns of quantum entanglement, invisible informational relationships connecting particles across the universe. Under this view, gravity, geometry, and perhaps even time may not be truly fundamental. They could emerge from deeper structures humans are only beginning to glimpse mathematically. Black holes sit directly at the center of these questions because they combine gravity, thermodynamics, entropy, quantum mechanics, and information into one object. They are where modern physics starts revealing its unfinished edges. And perhaps that is why Stephen Hawking's work became so influential beyond science itself. He transformed black holes from simple cosmic destroyers into clues pointing toward deeper layers of reality. Before Hawking, black holes largely represented endings. After Hawking, they became puzzles connected to the fundamental structure of the universe. Even now, decades later, many of those puzzles remain unresolved. Physicists still debate how information escapes black holes. Researchers continue searching for a theory uniting gravity with quantum mechanics completely. Some ideas involve holographic universes. Others involve quantum error correction, emergent spacetime, or structures still not fully understood. The closer science studies black holes, the less reality resembles the stable mechanical universe humans once imagined. And somewhere tonight, in the darkness between distant galaxies, a black hole may already be evaporating very slowly. Faint particles escaping from the edge of impossible gravity, mass disappearing one microscopic fraction at a time, quietly proving that even the darkest objects in existence may not be permanent after all. Because perhaps the strangest truth Hawking revealed is not that black holes emit radiation. It is that black holes may be trying to tell us the universe itself is built on principles far stranger than matter, stars, or space alone. On clear nights far away from city lights, the Milky Way can look peaceful, a pale river of stars stretching quietly across the sky. Ancient people saw it as a path for souls, a celestial ocean, a bridge between worlds. But hidden deep inside that glowing band of light is something almost impossible to imagine correctly. An invisible object so massive that millions of stars orbit around it. And the strange part is that our galaxy is not unusual. Modern astronomy now suggests that nearly every large galaxy in the universe may contain a supermassive black hole at its center. Not small black holes formed from dying stars, but gravitational giants containing millions or even billions of times the mass of the Sun. The one at the center of the Milky Way is called Sagittarius A star, pronounced Sagittarius A star. It lies roughly 26,000 light-years from Earth in the crowded core of our galaxy. No telescope can see the black hole directly because light cannot escape from it. Yet astronomers know it exists, for the same reason ancient sailors knew invisible winds existed over the ocean. They can observe the motion of everything around it. For decades, scientists tracked stars orbiting the galactic center at extraordinary speeds. Some completed enormous loops in only a few years, moving so fast that only an incredibly compact and massive object could explain their motion. One particular star, known as S2, helped provide some of the strongest evidence. Its orbit revealed that something roughly 4 million times the mass of the Sun was packed into a region smaller than our solar system. Nothing else known in astrophysics fits those conditions as convincingly as a supermassive black hole. And yet, Sagittarius A star is relatively modest compared to some of the monsters discovered elsewhere in the universe. Certain black holes are so enormous that ordinary comparisons stop feeling meaningful. One of the largest known examples, TON 618, may contain tens of billions of solar masses. Trying to emotionally picture something that massive becomes difficult because the human brain evolved to understand forests, storms, mountains, and oceans, not objects capable of outweighing entire star systems millions of times over. And these giants do not simply sit silently in darkness. When actively feeding, they become some of the brightest objects in existence. Matter spiraling toward a supermassive black hole forms an accretion disk, rotating at enormous speeds. Friction heats the material to extraordinary temperatures. Radiation erupts outward across space. In some cases, magnetic fields near the black hole launch gigantic jets of plasma traveling close to the speed of light for distances spanning entire galaxies. These active black holes create quasars. For a long time, quasars confused astronomers because they appeared unbelievably bright despite existing at extreme distances. Eventually, scientists realized the energy did not come from stars alone. It came from matter falling towards supermassive black holes. Incredibly, a single feeding black hole can outshine the combined light of billions of stars surrounding it. There is something deeply unsettling about that image. Entire galaxies illuminated by darkness at their center. But perhaps the most mysterious discovery came when astronomers began finding quasars in the early universe. Some existed less than 1 billion years after the Big Bang, and they already appeared enormous. This created a serious cosmological puzzle because, according to standard growth models, black holes should not have had enough time to become that massive so quickly. Growing a supermassive black hole is not simple. Radiation from infalling matter pushes outward, limiting how rapidly material can accumulate. Yet, some early quasars already contained black holes weighing billions of suns. It almost looked as if the universe accelerated their creation somehow. And that led to a disturbing possibility. Maybe black holes did not merely appear inside galaxies, Maybe galaxies formed around black holes. Several modern theories explore this idea. In some models, giant seed black holes formed early in cosmic history, pulling gas, dust, and stars inward over time until galaxies emerged around them. Under that interpretation, black holes stop looking like cosmic destroyers and begin resembling architects of galactic structure itself. The relationship between galaxies and black holes suddenly becomes less accidental. The deeper astronomers study galaxies, the more connected the two appear. Even today, the size of many supermassive black holes correlates closely with the size and behavior of their host galaxies. Somehow, despite existing on vastly different scales, galaxies and black holes seem to evolve together, and occasionally, those black holes awaken violently. At the center of most galaxies, including the Milky Way, supermassive black holes remain relatively quiet because they are not consuming large amounts of matter actively. Sagittarius A star currently feeds at a very low rate compared to bright quasars. If someone viewed our galaxy from millions of light years away, its center would appear fairly calm. But evidence suggests Sagittarius A star was not always so peaceful. Astronomers have discovered gigantic structures extending above and below the Milky Way, called the Fermi bubbles, enormous regions emitting high-energy radiation. Some scientists suspect they may be remnants of past energetic activity from the galactic center, possibly triggered when Sagittarius A star consumed large amounts of matter long ago. In other words, the quiet black hole at the center of our galaxy may once have been dramatically more active, and it could become active again someday. Fortunately, Earth lies far enough away that Sagittarius A star poses no immediate threat. But if the black hole suddenly began feeding aggressively, the center of the Milky Way could brighten enormously. Radiation levels would increase across the region. Jets of energetic particles might erupt outward. Entire sections of the galaxy could become hostile to life. The fact that our galaxy currently appears stable may be less permanent than it feels. That realization subtly changes the emotional meaning of the night sky. The stars overhead begin seeming less timeless and more dynamic, part of a larger galactic system, quietly shaped by invisible gravity over millions of years. Because supermassive black holes do more than consume matter, they may regulate the growth of galaxies themselves. Modern astrophysics increasingly suggests black holes influence how quickly stars form inside galaxies. Powerful radiation and plasma jets from active galactic nuclei can heat surrounding gas or even blow it outward entirely, preventing new stars from forming efficiently. This process, known as feedback, may help explain why some galaxies stop producing stars and become quieter over time. In a strange way, black holes may function almost like cosmic governors, controlling the pace of galactic evolution. Invisible objects shaping billions of suns across hundreds of thousands of light years. And sometimes, these giants do not remain anchored at galactic centers forever. When galaxies collide, their central black holes may eventually merge as well. During the final stages of that collision, gravitational waves ripple outward through spacetime itself. Under certain conditions, the newly merged black hole can receive a violent recoil kick from asymmetrical gravitational wave emission, potentially ejecting it from the galaxy entirely. Astronomers believe some rogue supermassive black holes may wander intergalactic space after such events. The image feels almost mythological, a dark object larger than millions of stars drifting invisibly through cosmic emptiness after being thrown from its home galaxy. And smaller rogue black holes may be vastly more common. The Milky Way alone could contain millions of unseen black holes moving silently between stars. Most would never reveal themselves unless they passed near gas clouds or gravitationally affected nearby objects. The universe humans see through visible light may represent only a fraction of what truly exists. Behind the glowing galaxies may hide an enormous invisible structure shaped by black holes, dark matter, and gravitational interactions humans cannot observe directly. That idea creates a strange emotional tension in modern astronomy. The more accurately science maps the cosmos, the more hidden the universe appears. Visible stars begin feeling almost superficial, bright decorations floating above deeper, unseen machinery. And somewhere tonight, near the center of a distant galaxy, a supermassive black hole may already be feeding slowly in darkness. Stars orbiting around invisible gravity, radiation curling through enormous magnetic fields, entire solar systems moving according to the pull of something they will never actually see, quietly reminding the universe that some of its largest structures may ultimately be shaped by objects built from darkness itself. Space often looks empty from a distance. Between stars, there are enormous regions of darkness where nothing seems to exist at all. Ancient humans imagined the night sky as a calm ceiling of lights suspended above Earth. Even modern astronomy, despite revealing billions of galaxies, still leaves people with the impression that space is mostly silent emptiness. But the deeper scientists study the universe, the less empty it appears. Somewhere tonight, there may be black holes moving invisibly through the Milky Way, with no stars orbiting them, no glowing accretion disks revealing their position, and no light escaping to announce their existence. Entire objects, heavier than suns, drifting silently through interstellar darkness like gravitational ghosts. And humanity might never notice most of them. One of the strangest things about black holes is that they do not always remain where they were born. When massive stars explode in supernovas, the explosions are not always perfectly symmetrical. If more force erupts in one direction than another, the collapsing remnant can receive an enormous kick through space. In some cases, the newly formed black hole may be launched away from its birthplace entirely. Astronomers call these objects rogue black holes. The idea feels unsettling because it transforms black holes from stationary cosmic traps into moving, invisible objects wandering through galaxies alone. Unlike stars, Rogue black holes emit almost no visible light unless actively feeding. A dark object several times heavier than the Sun could drift through space nearly undetectable, crossing between star systems silently for millions of years. And statistically, there may be enormous numbers of them. Some estimates suggest the Milky Way could contain millions, perhaps even hundreds of millions, of stellar black holes formed throughout galactic history. Most would remain hidden because detecting isolated black holes is extremely difficult. Astronomers usually find black holes indirectly, through X-rays from infalling matter, gravitational effects on nearby stars, or collisions generating detectable waves in spacetime. But a black hole traveling alone through empty regions of space may reveal almost nothing at all. That possibility changes the emotional feeling of the galaxy. The darkness between stars begins seeming less empty and more occupied by invisible mass humans cannot naturally perceive. Occasionally, however, black holes reveal themselves violently. When two black holes orbit each other closely, they slowly lose energy through gravitational radiation. Einstein predicted this phenomenon over a century ago as part of general relativity, though even he doubted humans would ever detect it directly. According to the theory, accelerating massive objects disturb spacetime itself, creating ripples moving outward at the speed of light. These ripples are called gravitational waves. For decades, they remained purely theoretical because the distortions reaching Earth are extraordinarily tiny. A passing gravitational wave changes distances by fractions smaller than atomic nuclei. Detecting such movements seemed almost impossible. Then, in 2015, humanity finally observed them. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected waves produced by two merging black holes roughly 1.3 billion light-years away. The signal lasted only a fraction of a second, but inside that brief vibration was evidence that space-time itself had physically stretched and compressed as the black holes collided. It was one of the most important confirmations of Einstein's work ever achieved. And strangely, humans experienced the discovery almost like hearing the universe for the first time. Scientists converted the gravitational wave signal into audio frequencies. The result was a short rising sound known as a chirp, a tiny upward sweep representing two black holes spiraling together before merging. It lasted less than a second, yet emotionally, it carried enormous weight. Human beings had not seen the collision directly. They had listened to the structure of space-time shaking. That realization altered astronomy permanently. Until then, nearly all observations of the universe relied on electromagnetic radiation, visible light, radio waves, X-rays, gamma rays. Gravitational waves opened an entirely new method of studying reality itself. The universe suddenly seemed less silent, and black holes became some of its loudest hidden objects. As black holes spiral closer together, their orbital speeds become extraordinary. In the final moments before collision, some may rotate around each other at significant fractions of the speed of light. Enormous amounts of energy pour outward through gravitational waves. For a brief instant, the merger can release more power than all the stars in the observable universe combined. Yet almost none of that energy appears as ordinary light. The violence happens mostly in darkness. There is something haunting about that contrast. Some of the largest events in existence unfolding invisibly across the cosmos. And collisions can produce another strange consequence. If gravitational waves are emitted unevenly during the merger, the newly formed black hole can receive a recoil kick powerful enough to eject it from its galaxy. Some simulations suggest supermassive black holes may be launched through intergalactic space at millions of miles per hour after violent mergers. Imagine an invisible object heavier than millions of stars traveling alone between galaxies, not hunting, not chasing, simply moving through darkness with unstoppable momentum. And smaller rogue black holes may occasionally pass through ordinary star systems without immediate detection. This possibility sounds frightening at first, but distances in space are enormous, making close encounters extremely rare. Still, astronomers believe isolated black holes likely drift throughout galaxies constantly. In 2022, researchers reported evidence of what may have been the first detected isolated stellar black hole moving through the Milky Way, based on gravitational lensing effects, the way its gravity bent light from stars behind it. Even detecting one such object required extraordinary precision. Most would remain invisible. That invisibility creates a strange psychological tension in modern astronomy. Human beings instinctively trust vision. If something cannot be seen, it feels less real emotionally. But black holes repeatedly force science to confront the opposite idea. Some of the most important structures in the universe may exist beyond ordinary visibility entirely. And not all black holes are gigantic. Some theoretical models suggest microscopic black holes may have formed shortly after the Big Bang. These primordial black holes could range from extremely small masses to much larger objects, depending on conditions in the early universe. Tiny black holes would evaporate rapidly through Hawking radiation, while larger ones might survive until today. So far, no confirmed primordial black holes have been observed directly. But scientists continue searching because such objects could potentially explain portions of dark matter, the mysterious invisible mass shaping galaxies throughout the universe. This is one reason black holes continue fascinating researchers beyond their dramatic reputation. They repeatedly appear connected to deeper, unanswered questions about cosmology itself. How much invisible mass exists in the universe? What happened shortly after the Big Bang? How does gravity behave under extreme conditions? What structures remain hidden beyond human detection? Black holes sit near all of these mysteries, and the more astronomy advances, the more the visible universe starts looking incomplete. Stars, planets, and galaxies may represent only the bright surface of something far larger and darker underneath. Even now, countless black holes likely move unnoticed across cosmic distances. Some orbit quietly inside binary systems. Others drift alone through interstellar darkness. Some merge violently, sending ripples through space-time itself. Others may have wandered for billions of years without interacting meaningfully with anything at all. The universe may already be filled with invisible motion humanity rarely perceives, and somewhere tonight, beyond the stars visible above Earth, another rogue black hole may already be crossing silently through the Milky Way. No light surrounding it, no warning announcing its approach, only gravity moving through darkness, carrying the remains of a dead star across the galaxy, while the rest of the universe continues shining around something almost completely unseen. Most people imagine the solar system as stable. The planets move in predictable paths. The sun rises every morning. The night sky changes slowly enough that human civilizations can build myths around repeating stars and seasons. Compared to the violence happening elsewhere in the universe, our corner of space feels strangely calm. But that calm depends on gravity remaining balanced, and black holes are capable of disturbing that balance without announcing themselves first. One of the biggest misconceptions about black holes comes from movies and popular culture. They are often portrayed as giant cosmic vacuum cleaners, pulling everything inward instantly. In reality, gravity behaves much more quietly than that. A black hole only becomes overwhelmingly dangerous when something moves extremely close to it. From far enough away, gravity from a black hole behaves almost exactly like gravity from any other object with the same mass. That means if the sun were somehow replaced overnight with a black hole of identical mass, Earth would not suddenly spiral inward. Our orbit would remain nearly unchanged because gravity at Earth's distance would stay essentially the same. The terrifying part is not what would happen to Earth's orbit, it is what would happen to Earth itself. Without sunlight, the planet would begin cooling almost immediately. Within days, average temperatures would start dropping rapidly. Photosynthesis would collapse across much of the surface. Plants would die. Food chains would destabilize. The skies would darken into something closer to permanent twilight. At first, oceans would continue retaining heat because water changes temperature slowly. Geothermal energy from Earth's interior would also provide limited warmth underground and deep beneath the sea. Certain microbial ecosystems near hydrothermal vents might survive for very long periods. But on the surface, civilization would begin freezing toward extinction. Not in one dramatic explosion, but slowly, quietly. The atmosphere itself would eventually begin changing. Ice would spread across continents and oceans. Vast regions of Earth could freeze solid over time. Humanity's survival would depend entirely on artificial energy systems, underground habitats, and technological adaptation. That scenario reveals something unsettling about life on Earth. The sun is not merely lighting our world. It is actively holding biological complexity together every second. And black holes expose how fragile that dependence really is. But replacing the sun with a black hole is only a thought experiment. A more realistic danger would involve a rogue black hole passing through or near the solar system. Fortunately, such encounters appear extremely rare. Space is enormous, and the distances between stars are difficult to emotionally grasp. Yet over cosmic timescales, stars, gas clouds, and possibly rogue black holes move constantly through the Milky Way. The solar system itself orbits the center of the galaxy at roughly 500,000 miles per hour. Nothing in the galaxy is truly standing still. If a black hole passed nearby, the first signs might not be visual at all. Instead, astronomers could notice subtle gravitational disturbances. Planetary orbits might shift slightly. Comets could begin changing trajectories. Objects in the distant Oort cloud, the enormous spherical region of icy bodies surrounding the solar system, might become destabilized. And those consequences could unfold slowly across thousands or even millions of years. That is part of what makes cosmic danger psychologically different from disasters on Earth. Human beings evolved to recognize immediate threats: predators, storms, fire, famine. But astronomical catastrophes often unfold gradually enough that the sky still appears calm, while gravity quietly reshapes everything underneath. The Oort cloud, for example, extends incredibly far beyond Pluto. It may contain trillions of icy objects weakly bound to the sun's gravity. A passing star or black hole could disturb some of those objects, sending comets inward toward the inner solar system. Scientists already believe gravitational interactions with nearby stars may occasionally trigger waves of long-period comets. A rogue black hole passing sufficiently close could theoretically create similar disturbances. The effect would not resemble Hollywood destruction. There would be no giant vortex appearing above Earth. Instead, danger could emerge years or centuries later as increased comet impacts slowly destabilized planetary conditions. Black holes often affect systems indirectly before directly. And if a black hole passed extremely close to a planet, the consequences could become much more violent. Gravity near compact massive objects changes rapidly with distance. This creates tidal forces, differences in gravitational pull across an object's structure. If those forces exceed the strength holding a planet together, the planet can literally begin tearing apart. Astronomers call this process tidal disruption. The effect has already been observed with stars. When a star drifts too near a supermassive black hole, gravity stretches it into long streams of glowing gas through a process similar to spaghettification. Some of the stellar material spirals inward, while the rest blasts outward into space, creating brilliant flares visible across galaxies. These events are known as tidal disruption events. In recent years, telescopes have observed several likely examples in distant galaxies, stars being shredded by invisible black holes. For a brief period, the black hole becomes dramatically brighter as it consumes the remains. The images are strangely beautiful and horrifying at the same time. A glowing river of destroyed starlight spiraling into darkness. And, importantly, the black hole does not need to physically collide with the star to destroy it. Gravity alone does the work. The same principle could theoretically apply to planets under extreme enough conditions. Earth itself would likely survive a distant black hole encounter if the object merely passed through the outer solar system. But closer interactions could destabilize orbits, alter climates, or eventually eject planets entirely from their normal paths around the Sun. That possibility changes the emotional meaning of planetary stability. Earth's orbit feels permanent because human civilization exists on very short timescales. But over billions of years, planetary systems remain vulnerable to encounters with wandering stars, molecular clouds, and possibly unseen black holes moving through the galaxy. And detecting such objects remains difficult. Black holes emit no light unless actively feeding, An isolated rogue black hole drifting through deep space may only reveal itself through gravitational lensing, the bending of background starlight, or through subtle orbital disturbances affecting nearby objects. In other words, an invisible object could theoretically move through large regions of space with almost no obvious visual signature. That idea naturally invites speculation about whether rogue black holes may have passed near the solar system in the distant past. Some researchers have explored whether unusual orbital patterns in outer solar system objects could hint at hidden massive bodies, though there is currently no scientific consensus linking any known extinction events or orbital anomalies directly to black holes. Still, the broader principle remains true. The solar system does not exist in isolation. It moves through a galaxy filled with invisible mass, wandering stars, magnetic fields, dark matter, and gravitational interactions unfolding across enormous spans of time. Stability in astronomy is often temporary rather than absolute. Even nearby stars occasionally pass relatively close to the solar system on cosmic scales. In about 1.3 million years, the star Gliese 710 is expected to pass through the outer Oort cloud region, likely disturbing comet trajectories significantly. Encounters like this remind astronomers that the solar system exists inside a dynamic gravitational environment, not a perfectly isolated bubble. Black holes simply represent the most extreme version of that reality. And emotionally, there is something humbling about realizing Earth survives partly because of orbital luck. The balance allowing oceans, climates, ecosystems, and civilization to exist depends on stable gravitational relationships maintained over immense periods of time. Black holes reveal how delicate those relationships truly are. Somewhere tonight, beyond the orbit of Neptune and far outside the visible planets, the solar system continues drifting through the Milky Way at enormous speed. Comets sleep in darkness at the edge of the sun's influence. Distant stars move silently against the galactic background. And somewhere beyond human sight, invisible objects may already be crossing through the same galaxy, carrying enough gravity to reshape worlds without emitting a single ray of light. If you could travel far enough away from Earth, beyond the solar system, beyond the Milky Way, beyond even the surrounding clusters of galaxies, the universe would begin looking less like a collection of stars and more like a vast, glowing web suspended inside darkness. Billions of galaxies scattered across unimaginable distances. Light traveling for billions of years before reaching human telescopes. Entire cosmic structures so enormous that the human brain struggles to emotionally process their scale. And yet, according to some physicists, even all of that may only be a tiny, visible fragment of something much larger. Because the deeper scientists studied black holes, the more uncomfortable similarities began appearing between black holes and the universe itself. One of the strangest parallels involves the idea of a singularity. According to standard cosmology, the observable universe began roughly 13.8 billion years ago in an extremely hot, dense state, commonly referred to as the Big Bang. Importantly, the Big Bang was not an explosion inside empty space. Space itself expanded outward from that early state. Time, matter, energy, and the geometry of the universe all evolved together from conditions modern physics still struggles to describe completely. And when scientists mathematically trace the expansion backward far enough, the equations approach something disturbingly familiar: a singularity. Just like the predicted center of a black hole, the early universe appears to converge toward a state of extreme density where current theories begin failing. Space and time themselves stop behaving normally. The equations collapse into infinities. That resemblance does not prove black holes and the Big Bang are identical phenomena, but it was strange enough to inspire a radical possibility. What if our universe itself emerged from something resembling a black hole? Several theoretical models have explored this idea over the years. In some versions, black holes may not end in singular destruction, but instead create new, expanding regions of spacetime internally. From the outside, the black hole appears finite and trapped behind an event horizon. But inside, conditions could potentially evolve into an entirely separate universe disconnected from the original one. Sometimes, these ideas are called baby universe theories, and emotionally, they change the meaning of black holes completely. Instead of cosmic graves, black holes begin resembling cosmic seeds. There is no scientific consensus supporting this interpretation yet. Many physicists remain skeptical, and observational evidence remains absent. But the reason the idea persists is because modern physics already encounters profound uncertainty near both singularities and the earliest moments of the universe. The mathematical overlap keeps reopening the question, and once that possibility enters the imagination, another unsettling thought follows naturally. If black holes can create universes, perhaps our universe was created the same way. That idea was explored in various forms by physicists such as Lee Smolin, who proposed concepts resembling cosmological natural selection. In simplified terms, universes capable of producing many black holes might generate more offspring universes over cosmic time. Under such speculative models, black holes become part of an evolutionary process operating at the scale of entire universes. The cosmos starts sounding less mechanical and more biological. Universes giving rise to other universes through gravitational collapse. Again, these ideas remain highly theoretical. But what makes them compelling is not certainty. It is the realization that black holes repeatedly force scientists to question assumptions once considered stable. And they do not stop at one universe. Modern cosmology already contains several serious multiverse theories independent of black holes. Some emerge from inflationary cosmology, the idea that the early universe expanded exponentially fast fractions of a second after the Big Bang. Certain inflation models suggest this expansion may continue eternally in different regions of spacetime, constantly creating isolated bubble universes with potentially different physical conditions. Under that picture, the observable universe becomes only one small pocket inside a vastly larger reality, possibly one among countless others. Some universes might contain different laws of physics entirely, different particle masses, different numbers of dimensions, different structures of matter. In many of them, stars may never form. Life may never emerge. Some may collapse instantly after forming. Others could remain forever dark. The universe humans experience might represent only a narrow region where conditions happened to permit complexity. That possibility feels both awe-inspiring and strangely lonely at the same time. And beneath all of these theories lies another unsettling realization. Empty space may not truly be empty at all. Quantum physics suggests the vacuum of space constantly fluctuates with microscopic activity. Virtual particles briefly emerge and disappear continuously. Energy fields ripple invisibly, even in regions humans would call nothingness. Some physicists describe spacetime at extremely tiny scales as a kind of quantum foam, a restless structure where geometry itself fluctuates chaotically. Reality may be far less solid and stable underneath than everyday experience suggests. And this leads to one of the most disturbing ideas in modern cosmology: vacuum decay. According to certain interpretations of quantum field theory, the vacuum state of our universe may not represent the absolute lowest energy state possible. It could instead exist in a metastable condition, temporarily stable, but not fundamentally permanent. If true, a transition to a lower energy vacuum state could theoretically occur somewhere in the universe through quantum tunneling. The result would be catastrophic beyond human comprehension. A bubble of new vacuum would expand outward at nearly the speed of light, rewriting the laws of physics inside it completely. Atoms, chemistry, stars, and biological structures as humans know them might no longer function. And because the bubble would move at light speed, no warning could ever arrive beforehand. The universe would simply change. Most physicists consider such scenarios extremely speculative and likely unimaginably rare, if possible at all. But the fact that serious scientific equations permit discussions like this reveals how fragile and uncertain modern cosmological understanding can become near the foundations of reality. And increasingly, some researchers suspect the deepest layer of reality may not even be matter itself. Information has started taking a strangely central role in theoretical physics. Black hole entropy, quantum entanglement, holographic principles all point toward the possibility that information may be more fundamental than space, time, or particles. In certain approaches to quantum gravity, space-time itself may emerge from informational relationships between quantum systems. Geometry becomes secondary. Space stops being the stage on which physics occurs and instead becomes something produced by deeper structures underneath. This is difficult to picture because human intuition evolved entirely inside emergent space-time if these theories are correct. Asking what exists beneath space may be like asking what lies north of the North Pole. The question itself may stop functioning normally. And black holes appear repeatedly at the center of these mysteries. They expose tensions between gravity and quantum mechanics. They challenge the meaning of information. They distort time. They blur the line between beginnings and endings. Again and again, black holes push physics toward the edges of comprehension, almost like cracks in reality, where deeper structures briefly become visible. Yet even with modern telescopes and equations, humans still observe only a limited portion of existence. The observable universe has a cosmic horizon defined by the distance light has traveled since the Big Bang. Beyond that horizon, more space almost certainly exists, but its light has not had enough time to reach Earth yet. In other words, humans literally cannot see the full universe, and perhaps never will. That limitation quietly reshapes the emotional meaning of cosmology. No matter how advanced science becomes, there may always remain structures larger than observation, older than evidence, or stranger than intuition can comfortably hold. Black holes force people to confront that uncertainty directly because they sit exactly where understanding starts dissolving into possibility. And somewhere tonight, beyond the farthest galaxies visible to human telescopes, reality may already extend into regions no civilization will ever observe completely. More space-time, more darkness, perhaps more universes entirely. And hidden somewhere inside that unimaginable scale, black holes may continue collapsing, forming, evaporating, and bending reality in ways still quietly shaping the deepest structure of existence itself. Far beyond the reach of Earth's telescopes, somewhere between distant galaxies, there may be a black hole drifting through complete darkness at this very moment. No light escapes from it. No image reveals what lies inside. Around it, space-time bends silently, while stars continue moving through the universe, almost unaware of the invisible gravity nearby. And, after more than a century of modern physics, humanity still does not truly know what exists beyond the event horizon. That uncertainty may be the final and most unsettling secret black holes leave behind. Science has mapped galaxies, measured the age of the universe, detected gravitational waves, photographed the shadow of a black hole, and tracked stars orbiting invisible objects millions of times heavier than the Sun. Yet every major discovery about black holes has carried a strange side effect. The closer humans move toward understanding them, the larger the unknown seems to become. Because no human being has ever seen inside a black hole, and according to current physics, no information from beyond the event horizon can directly return to observers outside. That boundary creates one of the hardest limits in all of science. Telescopes can study matter falling inward. Astronomers can observe radiation around black holes. Physicists can build mathematical models describing possible internal structures. But the region beyond the event horizon remains fundamentally hidden from direct observation. In a sense, black holes contain areas of reality permanently separated from human experience. That fact changes the emotional feeling of astronomy itself. Most scientific mysteries eventually shrink when better instruments appear. Mountains once hidden become mapped. Microscopic organisms become visible through lenses. Distant galaxies emerge through stronger telescopes. But black holes impose a deeper kind of invisibility built into space-time itself. And because of that, every theory describing their interiors remains incomplete. Modern physics currently rests on two astonishingly successful frameworks: general relativity and quantum mechanics. Relativity describes gravity, planets, stars, galaxies, and the large-scale structure of space-time with extraordinary precision. Quantum theory explains atomic and subatomic behavior equally well. Separately, both theories work beautifully. Together, they begin breaking apart near black holes. Inside singularities, relativity predicts infinities, infinite density, and infinite curvature of space-time. Quantum mechanics, meanwhile, treats nature probabilistically and resists those infinities. The two systems refuse to combine cleanly under extreme gravitational conditions, and black holes expose that incompatibility mercilessly. This is one reason physicists continue searching for a theory of quantum gravity, a framework capable of uniting gravity with quantum mechanics consistently. Some approaches involve string theory. Others explore loop quantum gravity or emergent spacetime concepts. But despite decades of effort, no universally accepted solution exists yet. Which means humanity may still be missing something fundamental about reality itself. Even gravity, the force most directly associated with black holes, remains strangely mysterious. Compared to the other fundamental forces of nature, gravity is astonishingly weak. A small magnet can overcome Earth's entire gravitational pull on a paperclip. Yet gravity dominates cosmic structure across galaxies and the observable universe. Scientists still do not fully understand why gravity behaves this way. Dark matter and dark energy complicate the picture even further. Galaxies rotate too quickly for visible matter alone to explain. The expansion of the universe is accelerating unexpectedly. Together, dark matter and dark energy appear to make up roughly 95% of the universe's total energy content. In other words, ordinary matter, stars, planets, gas clouds, oceans, forests, human beings, may represent only a tiny, visible fraction of reality. The universe humans directly experience could be mostly hidden, and black holes sit directly inside that hidden territory. Some physicists have even proposed that classical black holes may not exist exactly as currently imagined. Alternative theoretical objects such as gravastars, fuzzballs, or quantum-corrected compact objects attempt to solve certain paradoxes without requiring traditional singularities. These ideas remain speculative, but their existence reveals something important. Science still does not know with certainty what a black hole truly becomes under the most extreme conditions. Even the famous black hole image released by the Event Horizon Telescope in 2019 did not directly photograph the black hole itself. It captured the shadow surrounding it. The glowing ring in the image came from superheated matter and distorted light orbiting outside the event horizon. The dark center represented the absence created by trapped light paths. Humanity effectively photographed gravity-bending light around an invisible object, not the object itself. That subtle distinction matters because it reminds people how much of black hole science relies on indirect observation. Humans study black holes through consequences: orbital motion, radiation, lensing effects, gravitational waves, while the central reality remains hidden behind a boundary no signal crosses outward from. And perhaps much of the universe works similarly. Modern cosmology increasingly suggests humans observe only a narrow slice of existence. Visible matter appears vastly outnumbered by invisible dark matter. Cosmic acceleration hints at dark energy whose nature remains uncertain. Entire regions beyond the observable universe remain permanently unreachable because light from them has not had enough time to arrive since the Big Bang. Human beings may live inside only a small illuminated patch of a much larger structure. That realization changes how scientists think about the future of the universe as well. For much of the 20th century, many physicists assumed gravity would eventually slow cosmic expansion enough to trigger a future collapse called the Big Crunch. But discoveries in the late 1990s revealed the expansion is accelerating instead. No one knows with complete certainty what happens next. Some models predict a gradual heat death where stars burn out, galaxies fade, and the universe drifts toward increasing entropy and darkness over unimaginable timescales. Others explore more dramatic possibilities, like the Big Rip, where expansion eventually tears apart galaxies, stars, planets, and perhaps even atoms themselves. The long-term future of reality remains uncertain, but black holes may outlast almost everything else. Long after ordinary stars die, after galaxies become darker and colder, black holes could dominate the universe for periods almost impossible to emotionally grasp. Some calculations suggest supermassive black holes may survive for numbers of years written with over 100 digits before fully evaporating through Hawking radiation. This future era is sometimes called the black hole era, a cosmos where darkness becomes one of the last major structures remaining. And eventually, according to current theory, even black holes disappear. Hawking radiation slowly drains their mass across absurdly vast stretches of time until the final remnants evaporate away. After that, the universe may enter an even quieter stage, dominated by thin radiation and scattered particles drifting through expanding emptiness. No stars, no galaxies, possibly no recognizable structure at all, just increasing silence. There is something strangely peaceful and unsettling about that image simultaneously. Human history feels enormous emotionally because human lives are short. Entire civilizations rise and fall in tiny fractions of cosmic time. Black holes force people to confront scales so large that ordinary ideas of permanence begin dissolving completely. And maybe that is their deepest psychological effect. Black holes repeatedly remind humanity that understanding has limits. Not temporary technological limits alone, but perhaps cognitive ones as well. The human brain evolved for survival on the African savanna, not for intuitively grasping curved spacetime, quantum information, singularities, or cosmic horizons billions of light years wide. Science extends perception enormously, but the universe may still remain larger and stranger than human intuition can comfortably contain. Yet strangely, that uncertainty does not necessarily make the cosmos feel colder. In some ways, it makes it more beautiful, because black holes reveal a universe that still contains genuine mystery. Not mystery caused by ignorance alone, but mystery emerging from the structure of reality itself. The more carefully science studies the cosmos, the more the universe resists becoming simple. And somewhere tonight, beyond the visible stars above Earth, another black hole may already be waiting silently between galaxies. Gravity bending around invisible darkness. Time distorting near an unseen boundary, holding secrets no civilization has ever fully uncovered, quietly reminding the universe that even after everything humanity has learned, there are still places where knowledge itself disappears into the dark. Thanks for spending this time exploring the mysteries of black holes with me tonight. I hope this journey through the darkest parts of the universe helped you relax, wonder, and maybe see space a little differently. If you enjoyed the video, don't forget to subscribe and come back for more calm cosmic mysteries. Until next time, get some rest and keep looking up at the stars.